0.4. So from here you got that one, English safety factor for that one is 3.2. Simple not?
Yes.
Very simple. So I found out the size that I buy this one, you get the stress and everything from the simple loading. So maybe this, and then you do a second test. One hand only, one hand holding in the middle and two hands. Which one is more critical? And you compare. Oh, for this one, 3.2. For this one is maybe 2.1 only, 30 factor. So this is more critical than this. You can compare how's the loading. That is for 3.2, 3.2. Normal people, 3.2. If people is 100 kilogram, so maybe the certificator is 2.8 or still safe. Are you with me?
Yes.
Those kind of analysis is very simple. I just want you to look something, any product. Okay? There must be a size, whatever it is. Any product. You want to do a big design, you can go to the crane, whatever. Okay? You can size. Why the crane is the size like that? So what is the heaviest? On the capacity, they say the heaviest thing that can lift is how much? And then you know there's a limit. So that's the heaviest when you buy. You can look at the product of and then why they make the beam is so much that size. Where is the point of critical? In the middle or here, where? Or this one. Or this cross section here, what is the cross section? And then you do that bending, you do that one. And then you do that stress analysis, you do the Mohs circle and that one. And then you come up with from the information that they give. That is the maximum allowed load is that one. Because when you buy that one, they must be given the maximum allowed load, right?
Yes, yes.
Or you go to the bridge. You find out who designed this bridge. They said that one is the one being said the maximum load is 80 ton. You find out what is the size of the beam of the bridge. And do blah, 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 blah. Oh, the certificator is that one. Even though it puts 80 ton, that one, 80 ton with certificator already. Sometimes 8 ton only. Small rolly only can go. You find out what is the size of that one. And then you do the analysis. What kind of steel is that? Everything you do. Simple study actually. This is just engineers, just to train you to become engineers. Okay, small project. Each one of you must have, one group must have 4 people. So I'll give you 3 to 4 weeks before final exam. Maybe you can submit it 5 days before final exam. Final exam is 18 of February, right?
Yes.
So you can submit to me around 13 of February. Still about 3 or 4 more weeks for your group project. Okay? This is required by the faculty, by the school. Everybody have to do the project. So I think this is the simplest project, but it's a very good project for you to become an engineer. How to dig into the internet, how to dig the info, how to find the company, how not just see kayu, tak kenal kayu apa. See dia besi je tak kenal besi apa. Itu beza orang kampung dengan orang masuk universiti. Are you with me?
Yes. Then we need to write a report or what?
Exactly. You have to write a report. The final product is a report. A nice report, a picture, calculation, everything.
Okay.
Just one report for the 4 people. Okay?
Okay.
Okay. Thank you very much. Okay? For those who are not here, please inform them. If you know your friend is not here today. Okay? Okay, let us start today, our class today. With Al-Fatiha first. Al-Fatiha. Okay. Today we will continue, okay, on the work of the energy theory, okay. So yesterday we start about the energy theory, how to calculate the energy. The symbol is U from bending moment. Bending moment. Energy is moment square dx over 2EI. If energy from torsion, wait. Torsion square to what? Yesterday.
2GJ.
GJ. Why GJ? Because those are the properties. The torsion must be the shear properties. This is the shear properties, not the E. E is normal properties. This is all understanding, you know. If you memorize without understanding, you won't go anywhere. Why J? Because torsion is the area that's holding the torsion is J, not A. And then what is through the P? Axial loading. What's the energy? Must be the load square. What is the holding property there? Must be E and E. What is the shear load? V or Q? When the shear load of V or Q there must be a V or Q there. Q square or V square. Yeah, Q there. So what is the holding property there? Q is shear loading. Must be G, and then must be the area. Yeah? So let us do that. Is that true? Let us do that. And I ambil benda yang simple this one. This is 2 meter long. I put it 10 kilonewton load. Diameter is 50 mm. And the material is aluminium. The E is 70 gigapascal. Maybe it's too big, I don't know. Maybe it's not big, maybe too big, I don't know. Just try it first, okay? We don't want the stress to be higher than the yield, correct?
Yes, correct.
Higher than the yield, so that means it's not in elastic properties. We want to have to be in elastic properties, okay? Just to double check, what is the sigma there? P over A. What is that? 10 kilonewton divided by the area. Solid 50. 5, 50, 10 to the power minus 3 square over 4. Pi d square over 4. So what is the value there, please? Rough. Yeah?
5.09 megapascal.
5.09 megapascal. So no problem. So still below the yield, right? So aluminium, usually the yield is what? Aluminium varies. Some are strong aluminium higher than steel, maybe 300 megapascal. Some aluminium are less than steel, maybe only 150 megapascal. Are you with me, guys?
Yes.
So, but it is still below, right? Yeah? Well, even though it's below, we want to calculate that energy. How much energy? When this one is being pulled, so there must be elongation there. When elongation, there must be a spring there. Spring, the whole thing elongate, not just the end point, the whole thing elongate there. So, there must be a delta now. Forget about the delta now. How to do this? Energy is being stored when we pull the thing like a spring. That one, how do you calculate it? P squared. Integration of P squared dx. So this is what I call dx. You cut a very small distance. That one. So this is dx, and then you integrate it from 0 until 2. Are you with me? That one. This is what I mean x here, from 0 until 2. Are you with me?
Yes.
So when you cut in the middle there, all the load is P. Here also P. So the value is constant P all the way from 0 until 2 there. That's how you do that one. And then 2 EA. 2 EA, right?
Yes.
So you put that. So your P is 10 kilonewton. The kilo is 1000. 10 kilonewton. Newton square. Don't forget the square. And then integrate it from 0 dx, yeah, from 0 to 2. And then you have E. Your E is 70 giga, 10 to the power of 9. And then your area is pi 50 there. 0.050 square over 4. Yeah? Whatever value that one, this is constant, right? Then you integrate into dx, you got x, right?
Yes.
You got a value here, what? 10 to the power of 3 square, and then x, that one. And then 70, 10 to the power of 9, and then pi 0.050 to the square over 4, and then you x here from 0 until 2. So here, when 0 until 2 is 2 minus 0, right? So what is the value there? Let's do this calculation now to make you confident.
No, then the bottom one we should have 1, 2, right? 2 EA ma.
Oh yes, correct. 2 at the bottom there. And then you put that 2 minus 0, that one. Then you got the value there. What is the value there? We can always check the unit, that one. P square. Why you need a P? Newton. Square. Why you need X? Meter. Why you need of E? Gigapascal. Pascal is Newton per meter square. Correct?
Yes.
What is your unit of area? Meter square. So what do we have there? Meter square cancel. Newton cancel, Newton cancel. You got, at the end you got Newton meter. Newton meter is a unit of energy. Correct not?
Yes.
Joule. In electrical we call joule. I don't like to call joule. I like to call Newton meter because mechanical talking about the original unit. Joule is not original unit, right? We cannot have a feeling. What is 500 joule? Can you have a feeling? No. 500 Newton meter, you have a feeling. Yeah? So the unit is Newton meter then. What's the value again?
I calculate, I get 0.728.
0.728.
Ah.
The unit Newton meter. No. Newton meter.
Yes. I calculate again. I'm not sure.
How about the others?
Same as the same.
Okay. See that? Very small. 0.728 Newton meter. See that? 10 kilonewton meter, kilonewton, not kilonewton meter. That 10 kilonewton. If we pull that one, energy stored inside here is very small. Can you see that?
Yes.
Now you have a feeling, huh? Yeah? Now, let us do some other things. Huh? Okay. I have a same beam, that one. I give a pure moment. 10 kilonewton meter. This is 2 meter there. When I bend things, there must be energy stored inside, right?
Yes.
So can we calculate it? What is the energy stored, that one? Moment square dx. So I integrate the moment from 0 until 2. From 0 until 2 EI. Yeah, very nice, eh? And then moment 10 kilonewton, the same thing. Integrate, this is constant, no problem. Integrate with the x. So what you have there? 10 to the power of 3 square, and then must be x there. From 0 until 2. And then the bottom one, 2 EI. 10, 2 times 70, 10 to the power of 9. I is for diameter 50. What is I? pi 0.05 square pi d to the power 4 of 64. Do you remember that one not?
Yes.
And then you put the value there, that this is 2 minus 0 here. So what is the value there? Everybody try to calculate.
4.656 kilonewton meter.
Kilonewton meter, right?
Yes.
Just now it's not kilonewton, right? Newton meter, right?
Ah.
This is kilo. So now is 4656 Newton meter. 4001. This is less than 1 there. Can you see the difference there?
Yes.
Big or small?
D.
Very big. See that? When you give a moment, energy being stored is very much. When you give an axial loading, energy stored is not that much. Are you with me?
Yes.
One is 10,000 kilonewton meter. The other one is 10,000 kilonewton. Same number, yeah? But energy store very small. Energy store during the bending is how many? 4,000 more, you know? More than 4,000. This is 6,000 more. Times something that one become 1, times something become 1, become 6,000 more than 0.7 and 4,000. That's why the axial loading energy store is very small. Can be neglected. But energy store during the moment cannot be neglected. Are you with me?
Yes.
Okay. Look, some further things. Torsion. Torsion there. Put a torsion there and put a torsion there. Torsion is also 10 kilonewton meter. How much energy is that? Torsion is 10 kilonewton. Twist it. So there must be energy stored during that one. So how much that? Remember the formula T square. This is what? G.
J.
Energy from torsion. So energy T square, the same thing. 10 kilonewton meter square. Integrate, you got X. From 0 until 2, the length is 2 meter. And then the G is not 70. G volume is what? Around 30, 40. 10 to the power of 9. Because the E is 70, the G is, let's say, 40. And then the J, 5D to the 4 over 32. Yeah? This is 4656 Newton meter for bending. Now energy for torsion. What is the value there?
4074 Newton meter.
407 Newton meter. Can you see that? 4,000, also 4,000. Is that big energy not? Yes, energy being stored during torsion is much. Are you with me, guys?
Yes.
This is how you do to make you understand. If not, you don't understand. Yeah? And then you do a simple thing there. Then put load there. Cut section there. Have a V not.
Yes.
10 kilonewton. The V is 10 kilonewton not. All the way here is 10 kilonewton not.
Yes.
Shear force, right? So now you want to calculate energy from the Q or the V. So there must be Q square or V square. Same thing, 10 kilonewton square. Integrate, you got X square. Not X square, X. And then you got integrate from 0 until 2. This 2 meter there. 0 until 2. And then not GJ. What is that? For Q. GA. So 2G, the G there, the A is pi D to the square over 4. Pi D square over 4 is area. Yeah? So what is the value there?
1.27 Newton meter.
1.27 Newton meter, right?
Mm.
See that? Almost not very far away from axial loading, right?
Yes.
Very small compared to the torsion and moment. Okay, clear?
Clear.
Now look some more. It's all from doing some example exercise more and more and more and more, and then you understand what the formula is all about. So what about this? Same thing just now. I want to look the all type of energy there. There are 4 type of loading. Remember, axial, shear, moment, and torsion. Put a 10 kilonewton meter there. 10 kilonewton load. That's 2 meter there. We have calculated the Q now. What are other energy we have here? Forget about energy. What are the other loading we have here?
We have shear, we have moment.
Exactly. Now you see that? You cut X there. You got a moment now. Your moment is 10 to the power of 3 times X, right?
Yes.
Change 0 moment here and 20 kilonewton meter there, right? So the position from each one is changing, not?
Changing.
Changing. 10x or 10 kilonewton x, right?
Yes.
Yes. Then, what is that? What is the total energy? This is the nice thing about the integration. Look again. Look again. The moment is px. Moment is equal to px, if that is p. So your p now is 10,000 or 10 to the power of 3x. So it depends on x now. How you know that one? Do a cut section. Cut section, you know the general equation there. You know the V is constant, 10. Your moment is not constant, 10 times x, right?
Yes.
You know that one. How you know that one? From the free body diagram. You cut section, you know the loading and the moment there. So the nice thing about the equation, why we have that integration, the general equation, the integration, why is that? Energy from bending moment there. M squared dx over 2EI. What is M squared now? Your M is not constant 10 anymore. So your moment is 10x, right?
Yes.
Now your 10x squared. 10,000, 10 to the power 3, and then another x there. And then you square. What do we have there? Do that one first before the integration. What is the value there? 10 to the power of 6, right? And then x squared, right? X squared, right?
10k square.
Excuse me?
10k square.
Yeah, like 10k square. Your 10k you square, you get 10 to the power of 6, right? Your x you square it, you get x square, right? 10 to the power of 3, you square it. What you have there, man? This is 10 to the power of 6, right?
100.
Is it true?
100 mega. One k square we got 1 to the power of 10 to the power of 6.
Oh, we have 10k. Okay, 10. Okay. So you got 100 because we got 10. Not 1, right?
Yes.
So this is 100 mega. So 100 mega. And then x becomes square, right?
Yes.
And then 2EI in the bottom. And then you do that. This is the purpose, the integration there. Even though this is not constant, we can only calculate that. See, what do we have there? X square integrate, what do we have? 110 to the power of 6. X square integrate, what do you have?
1/3 of 10 to the
X
power of 2. X to
X
power
X
3.
to power of 3 divided by 3, right?
Yes.
3. There's 3 at the bottom there, and then 2 at the bottom there, and then E there. E is 70, 10 to the power of 9, and then I. I is what? Sorry, this is bending moment. Bending moment is I. Pi 0.050 to the power 4 over 64. So integrate, this is already integrated. You integrate it from x squared become x cubed, and then 2ei there, and then from 0 until 2, right? Your x is from 0 until 2, right? Right here from 0 until 2, right? So what is the value there? 2 to the power 3 is 8, right?
Yes.
8. So 110 to the power 6 times 2 to the power of 3 minus 0, and then you got the bottom there. 3 times 2 times 70 times to the power 9. I find 0.050 to the power 4 over 64. So what is the value there? These are the energy there, because changing from 0, increasing a little bit, until here is 20 kilonewton meter. So not constant. Even though it's not constant there, can we calculate it? Yes. Just now we have a beam like that, constant, 10 kilonewton meter. Here 10, 10, 10, 10, 10, 10, 10, 10. Now here is 0 here and 10 there. It's changing not? Changing. This is not changing. Definitely this value is less than this one. This one we got just now 4,000 plus, right?
Yes.
This one must be less than 4,000 plus, because this is not everywhere is for 10 kilonewton meter. It's like that, 0 until 10. Okay, what's the value there?
I need to calculate again. I got 6,000 something. Higher than the 10 kilonewton here.
Oh, sorry. I'm sorry. This is 10 kilonewton all over, right?
Yes, constant.
This is not 10. This is 20, you know. 10 times 2 is 20. 0 here, 20 here. Because distance is 2, right?
Yes.
So can be this higher than this? Can, because this is higher than 10, right?
Yes.
Just prove the one. What is the calculation there? What is the value there?
6209 Newton meter.
What is that again?
6209.
209.
Yes.
Newton meter.
6209.
6.
209.
6.
6209.
Cannot hear you again?
6209 Newton meter.
Okay, 6. Okay. What about the others? Is it correct?
Yes, yes, sir.
Jadi, see that? 4,000. The bending moment now for 10 kilonewton there is 62 Newton. Definitely we cannot compare because it's different, right?
Yes.
That is different from here. We cannot compare. This is bending shear point load here 10 kilonewton, and the bending moment here is 20 kilonewton meter. So there's constant everywhere here, only 10 kilonewton meter. So this is 0 until 20. So definitely different, right?
Yes.
So 6,000, 6209 Newton meter. See that? Big not? Very big compared to the axial and shear. The nice thing is that even though it's changing, can we calculate? Yes. Are you with me, guys? Okay. We can calculate the energy. Okay, all the energy are in terms of Newton meter. Kalau tak percaya, cuba kita calculate balik. Betul tak? M square dx integrate EI. We have calculated just now Newton meter. Now we got T square dx over 2GJ. What's the value? T square, T Newton meter, square, Newton meter, dx meter, right? And then G is Newton over meter square, right? J is meter to the power 4, right?
Yes.
Square there, and then to the power 4 become 2 now. And then meter 2 and 2 cancel out. Newton and Newton. So you got the Newton and meter there. Are you with me?
Yes.
Look at the Q there. Q square dx integrate over 2GA. Look at that. What's the unit there? What unit? Q is Newton. Newton square. X is meter. And then G is Newton over meter square. Area is meter square. Cancel out. Newton and Newton. So, Newton meter not?
Yes, Newton meter.
Exactly. And then you do the load. P square dx 2EA. Same thing. P is Newton. Square. X is meter. And then E is Newton over meter square. And then area is meter square. Cancel. So the what's left? Newton meter. So all are unit energy. Are you with me, guys?
Yes.
Okay. And then let us have a look at the nice thing. What about this? 100 Newton, 300 Newton. So this one is 200 Newton. Nampak tak?
Nampak?
So from A to B, the load is what?
100.
Yes, 100.
Mana ada? Kamu tak pandai free body diagram lah. Hancur lah macam ni. Cut dia.
I.
200 dah. What's the load dah?
200.
Mana ada 100? Cut here. Baru ada tak? Baru tak ada 100. 300 dah, 100 dah. Ada tak 100 dah?
Yes.
Here, 200. You see that? You miss your static, you fail your static, you fail your free body diagram. You are now in the second year, and then become third year next semester, and then you still don't understand what is free body diagram. Shame on you become an engineer. Forget. You know this thing because you don't know. It's not that you don't know. Forget. Correct me not?
Yes.
You fail your static. Your ilmu static is in the book. It's not with you. This is what I call people who have thinking and have to memorize the ilmu. Two different things. And to recall back the ilmu, semua ni budak sekolah menengah. Tak layak jadi engineer. Sayang. Faham tak ni?
Faham.
You nak masuk ilmu tu dah within you. Tengok dah tahu dah. Lepas tu saya detect tadi. Saja saya buat example ni nak detect siapa yang smart, siapa yang belum smart. Saya cakap apa kat sini? Mentang-mentang kamu nampak 300, 200 ni, you terus jump into conclusion. 100. Ini namanya budak sekolah punya mata. Dengar saya cakap ni? Mentang-mentang dia nampak 200 dengan 300 kat itu, terus dia cakap 100. Forget about the procedure, how to find the load section by section. There must be cut section there. Only then you know. Have you done that cut section? You haven't done the process of cut section. You jump into conclusion just by looking 300 and 200. Ni beza dia orang masuk universiti dengan tak masuk universiti. Faham sayang? I keep showing this to you. Your mistake ni I keep showing to you because I don't want you to be like that. Because so many people are rubbish. Just say what they see. The intelligence is not working. Just say what they see. They see 300 and 200. The answer is 100. Without intelligence. Faham sayang? Ini yang sebab saya jerit-jerit selalu nak tunjuk kat kamu kat mana error kamu. Okay, now 200 dah, 300 dah. So from A to B, what is force AB? Force AB is 200 compression, right? Cut. What is force from B to C? Force AB to C is 100 tensile, right?
Yes.
So, energy, whether it is compressed or tensile, it doesn't have effect because both are energy. It's not positive negative. Kalau tak percaya, masukkan dalam tu. Sebab the formula dia square. Are you with me not?
Yes.
When the square then negative 200 and 200 square sama tak nilai dia?
Sama.
Formula itself will betulkan balik. Are you with me?
Yes.
So dalam case ni, how do you calculate energy? You must do the cut section there. Cut section. So this is 200. So here is what is force AB. You do a force AB is equal to 200 Newton meter. Wow, this compression. So compression. You make that one, you cut that one, and then you decide that one. After you do all that work, what is the total energy there? Total energy ABC is equal to energy AB plus energy BC. Energy AB here, integration from, let's say the distance is, this is 2 meter, this is 1.5 meter. So 0 until 1.5 meter, the load is 200, negative 200 Newton, but square there. Cancel out not?
Yes, cancel.
Yes, and then integration into dx, you got x, and you got EA, that one, 2EA, and then plus another one, moment, the value here is 100 tensile square, and then integrate into dx again, but the integration is 0 to 2 because second one is 2, the first one is 0, 1.5, 2EA. So, can we calculate it, MG not?
Yes.
Yes. Even though the load is different section, different size, A different not? Yes, different size, all can be break into section that you can calculate them. Are you with me, guys?
Yes.
That's how you do the work. Okay. Now, we go further. Ini basic. Kita dah pergi. We have done this so many times. This example. 10 kilonewton. This is 1 meter, this is 2 meter. A to B is 1 meter. 2 meter lah. 2 meter, this is 3 meter. You see that?
Yes.
Yeah, let's say the diameter is 100 mm. Okay.
Doctor, can you move up a bit?
Okay, thank you. Sorry. Yeah. The load is, remember that, the L shape, we have done so many times, this one,
Yes.
X, Y, Z. So from A to B, what kind of loading do we have inside A and B?
Shear and moment, bending moment.
Good. That from B to C, what kind of loading we have inside here?
Shear and torsion.
Bending?
And moment.
Here we have two, bending moment and shear. Here we have a bending moment, we have a torsion, we have a shear. And this is what you say when you have a free body diagram in your head. Up until now, the free body diagram must be in your head. Must be correctly in your head. Yeah? How do we know that? Cut section there, you got that one. This is 10 kilonewton. 10 kilonewton. Okay, kilonewton. This is your X. That's your moment there. Your X is that one. My moment is equal to, let's say, put P there. Your P is 10 now. PX lah. P. 10 kilonewton. So 10 kilo letak. Tak payah tahu kilo lah senang Biar senang nak calculation kamu. 10X. Boleh?
Boleh.
10 only, 10 Newton. To make life easier lah. Okay, 10X. Tapi 10, kalau 10X, diameter besar tak boleh juga. Tak nampak energi tu. Okay, letak kilo juga. Tak practical. 3 meter long, 2 meter long, size 100 mm. Besar tu. Letak dengan 10 kilogram. Tak berbaloi, right?
Yes.
Not 10 kilogram, 1 kilogram. 10 Newton is 1 kilogram. So So tak berbaloi. Letak 10 kilonewton juga. 10 kilonewton that one. Okay, we want to see the value there. 10. So 10 to the power of 3x. You got x there. And then you got a v, no? You got a v. Your v is 10 kilonewton. Then cut there. Cut there. This is your x. Your x from B to C. That's my moment there. That's my torsion there. My moment here and my torsion is there. With my load 10 there. 10 to the power 3. This is 2. This is your x now. I cut it somewhere there. From x0 until x until 3. So my torsion is what? My torsion is 2 times
10 to the power of 3.
that one. 10 kilonewton. Constant.
That's 10.
Everywhere there. But my moment is changing. My moment is 10 to the power 3 times x. The moment is changing. Torsion is constant. My V there, my V also is constant. My V is also 10 to the power 3. So can I calculate, can I integrate each one of them?
Yes, can.
Yes. Energy AB from moment and shear. And then energy from B to C. Moment, shear and torsion. Add it all. That's how you do your things. Are you with me, guys?
Yes.
Yeah? So, macam mana nak buat tadi tu? Free body diagram. Each section inside tu apa load. Whether constant or depend on X. This all from static. Okay? Akhirnya energy total is equal to energy AB plus energy BC. This break into 2. Energy AB bending moment. This is energy AB Q. This is break into 3. Energy from bending moment, energy from torsion, energy from Q. See that? Plus. Dapatlah total energy tak?
Yes, can.
Oh, you can see from your calculation, energy Q is so small. Q is so small. This big. Campur pun tak masuk dalam calculation pun. Okay guys, clear?
It's clear.
Lot of things loading all can be calculated. Ni. Tekan dulu kat sini. Can I find energy there?
Yes.
Yes. AB apa load dia? Ni BC apa load dia? Can we calculate it?
Yes.
Yes. Moment dia. Ada tak load? Yes. The V. Ada tak bending moment? Yes. Bending moment is changing. How to integrate it? You can do all sort of work there. Okay guys, So dalam kepala kita, 2 can be neglected. Apa dia? Axial and V or Q, because we have proven it's too small. But bending energy from torsion and bending moment is very high compared to the shear and axial loading. But if you ask to calculate, you can always calculate even though it's small. Okay. Thank you for today. We continue next class. Remember that we have to do our project work, group work. You can select and then you can put your group name. Select your team member. Each group 1, group 2, group 3, group 4. Put your name there. You can discuss among you. Okay. Maybe this week these few days you can select your group member. And you can start the work. The work is not that much actually. I just want you to know how to be in a group. How you can communicate with other people. How can you divide the work. These are all the work of engineers. Are you with me? How can you search? These are all the work of engineers. And this is what I want you to have. That experience. Okay guys. Okay. Our next class is on Tuesday. Sunday, I was in KL. I will be in KL. Okay, the wedding of my daughter on the groom side. Okay, so we see you on Tuesday at 3 o'clock, right? In the afternoon.
Yes, 3 o'clock.
3 o'clock. Okay, 3 o'clock, and Wednesday we got class also, and then Wednesday night we have a test. So before that, you can ask me anything. You can PM me, ask me anything you want to discuss about the test too. Okay, you must continue to do the past year question and don't forget to review each one of your exercise from failure theory. Remember the failure theory, we have to cover back on the stress strain analysis, not? Definitely. Betul tak?
Yes.
You define the maximum stress, all chapter 1. Only then you can do a failure theory. So that cannot be run away for the rest of your life. Not just for this subject, for the rest of your life. You're working, you're doing that one also. You cannot put it aside. That static, you cannot put aside. You're going to use it every single day. The solid, cannot put aside. The solid 2 design cannot put aside. You use it every single day in your life when you work as an engineer. Okay, good luck. I give you some exercise for the homework and maybe do the past year test also for the weekend. Okay, thank you very much. Assalamualaikum.
Okay.